What's up, everybody? We're back on Mr. Murray's Mathland and continuing in another video in this series focusing on AP Calculus AB FRQ, Free Response Question Review. And, one of the 6 questions is often what I would call sort of a generic calculus problem where they give you an equation or a table or a graph, and they just kind of ask you a bunch of generic kind of calculus questions with it. Do some calculus, prove you've learned some things from throughout the year. And this specific one is going to focus on implicit relations. So let's just jump right in. So part A says, find dy dx for this implicit relation. So we say implicit because it is not expressed as f of x equals or y equals. So it's got, you notice, some y squared in there, and that later in the equation here we have 8y. And so when you want to find dy dx, the derivative, we're going to differentiate with respect to x. Right? So we're using some implicit differentiation here. So I'm going to differentiate each side of the equation with respect to x. And if you were, on the AP exam, you could skip this step and just go right into the very next step, which is taking the derivative of each side. But since this is kind of an instructional video, I'm going to try to show every little thing here and hopefully brush up on your implicit differentiation skills. So now going through here, if you're taking the derivative with respect to x, you want to pay attention to your variables you're dealing with. And if anything is not x, such as this, then you have to multiply by dy dx or y prime. Anything that is x, anything that matches that variable, that's just sort of normal differentiation as you're used to. So here we go. I'll just go right into it. Derivative of y squared, that would be 2y to the first, and then times y prime, or dy dx. You're really using the chain rule, multiplying by the derivative of that inner expression. And then derivative of minus 2x, that's going to be minus 4x. The derivative of 12x, that is 12. Derivative of 8y, watch out, that's a y, not x, is going to give you 8 times dy dx, or y prime, which is an acceptable, equivalent notation if you like. If you prefer doing that, it's a little less cumbersome to write. The derivative of 3, or any constant, is 0. And now when they say find dy dx, they mean solve for dy dx, have an, and isolate it, solve for it. And so we're going to do just a little algebra now to get dy dx alone. And so we're going to have what I call a dy dx party. We're going to group everything that has dy dx on one side of the equation. So these two terms that have dy dx, keep them on the left. Anything that doesn't have dy dx, you're not invited to the dy dx party. Move it to the other side of the equation. So I'm going to add 4x to the other side, subtract 12. And now that everything on the left has dy dx, I'm going to factor it out. So I can factor out y prime, or dy dx, and I'll have 2y plus 8. And over there on the other side, still 4x minus 12. And by the way, as you're doing this, we said certain steps could be skipped. Like you could skip this step and kind of go right into that differentiation step. Likewise, if you feel comfortable with your algebra, you could probably skip this whole step if you can do that, maneuvering and factoring out and go right to here. There's leeway with what you show. But it should be, stated that some FRQs, they tell you for a problem like this, dy dx is, and they'll give you what it is, and they'll say show that or prove that dy dx is this. So then it becomes more like a proof where you really don't want to skip too many steps, because that's the whole point, is to show and illustrate So just talking about these things along the way is just all overall review of things that come up on FRQs. And now to solve for dy dx, you're just going to divide by that quantity of 2y plus 8, right? It's just a big algebra game at that point. So when I divide by 2y plus 8, dy dx has now been solved for. There we go. You also may notice that that does reduce, but you don't need to reduce your answers or simplify your answers in any way on the FRQ. But if you're, like to, just for completeness, all of these terms are divisible by 2. If you want to think of the greatest common factor you can take out of everything, so it could be reduced to 2x minus 6 over y plus 4 if you divide everything by 2. Okay, so there we go. Part A, pretty standard FRQ type of problem right there. Let's look at part B. It says consider, same curve, but part B says use the line tangent to the curve at 1, -7 to estimate the y-coordinate of the point on the curve when x is equal to 2. So, if you haven't done one of these in a while or thought about this, this is a fairly common thing, but there's a couple different things going on in this question. One, it says use the line tangent to this curve at 1, -7. That's your first part of the problem. Write the equation of that tangent line. If you've come this far in calculus, you've probably written a lot of tangent lines. And as I always say in my class to my students, if we want to write a tangent line, just remember you need 2 things, the point and the slope, the point of tangency and the slope. And you have the point is 1, -7, so you just need the slope. And the slope is where the derivative comes in. So the derivative, as you may recall from the last step, dy dx is 2x minus 6 over y plus 4. You would not need to, reprove or even reestablish what dy dx is on the FRQ. It's a continuation. But remember, that's just the derivative. If you want the slope at 1, -7, you got to plug 1, -7 into that. So I'm going to substitute. Just be careful. You plug 1 in for x and -7 in for y, and that does reduce there to -4 over -3 or positive 4/3. That is your slope of your tangent line that you're looking for. So your point is 1, -7, your slope is 4/3, so here is your tangent line, or at least one version of it. Y plus 7 equals 4/3 times x minus 1. So there's the tangent line, and now it says use that to estimate the y-coordinate of the point on the curve when x is equal to 2. So this is your classic tangent line approximation kind of thing. Sometimes they phrase it a little differently, but usually to do this, you'd want to isolate y if you haven't already done so. Usually I wouldn't bother distributing that 4/3, but you could if you felt like it. And so here's where this represents the line, but we want the y value on the curve. So what we're doing now is we're going to say y, the y value we're looking for is approximately what the y value I would get from this line is when x is 2. So when x is 2, substitute 2 into that line for x, and you really don't even have to simplify. Again, you could leave your whole answer like that if you really wanted. You're in a rush, you're moving on, time is of the essence on the AP exam, but for completeness here, 2 minus 1 is 1, 1 times 4/3, 4/3 is 4/3, 4/3 minus 7. I mean, you could leave your answer like that. You could then, make a little common denominator and do 4/3 minus 21/3 and get -17/3. But in any event, that's the y-coordinate on the curve would be approximately -17/3. That's the y value you got from your line, and that's our best estimation of what the curve's y value would be. Okay, let's talk about part C now. Let's take a look. Something else that might possibly be asked. Oftentimes when you write a tangent line, they might, and you use it to approximate some value on the function, they might often ask you about the validity of that estimation. Is it an over or underestimate? And hopefully you know that that is related to the concavity of the graph. If the graph is concave up, a tangent line will always be an underestimate. If your graph is concave down, your tangent lines are always going to be, above the curve, except at those points of tangency. So they're going to be an overestimate. So you need to know about the concavity of the function. And that's why they've explicitly given you this. Sometimes they make you find it on your own. But we have the second derivative right here, this big elaborate fraction, and it says use this to determine if it's an over or underestimate. So we're going to take that same derivative here. Let's not, again, if you were doing the FRQ, you would have all this right in front of you. So dy dx is 2x minus 6 over y plus 4. And we now have that the second derivative, I guess I didn't need to reestablish what the first derivative was, is that, but I really want to take that point of tangency, and the point of tangency is what I use to construct that tangent line, and that's what I'm basing my estimate on. So you really need to use, I would say, that point of tangency from part B, 1, -7, that you use to write that tangent line. And you want to substitute that into the second derivative here. So everywhere I see y, I'm going to plug -7. Everywhere I see x, I'm going to plug in 1. And again, I really just need to know about the concavity, so I just need to know if the second derivative is positive or negative. And if you can tell that just by looking at it, then just say it. This is positive, this is negative, therefore blah, blah, blah. Sometimes you need to simplify a little bit to, be able to determine that in your head. If you do just keep going with this and you simplify, that's going to be -49 when you square -7 times 2 is going to be 98 minus 16 times 7 is going to be 70, and 42 is going to be 112 minus 2 plus 38. It's all going to be divided by -3 cubed, or -27. When we do combine those terms in the top, you can probably see that that's going to be positive, and in fact it's going to be positive 22 over -27, which the most important thing is that is less than 0. You have a negative second derivative, which tells you that your curve is concave down. I don't know if that's necessary to really say that, as long as you cite that the second derivative is negative. That's what we were really after. Don't leave any room for doubt in the graders' minds. Second derivative is negative, therefore the curve is concave down. Therefore, this tangent line is going to be, and if you'd like to draw a picture to convince yourself, your tangent line is going to be an overestimate that you got. So your final answer here is your tangent line will overestimate that y coordinate. Okay, and you can, use symbols and arrows, or, if you don't want to write, you can use abbreviations if you don't want to write full, complete sentences. But as long as the major terms or the terminology, and you don't just say things like it is positive, and it is increasing, and it's this, just make it clear, but communicate, and there's a lot of leeway with how you express these. And so we just did parts A, B, and C of this. I got a couple more, but I think it always helps if you can visualize what's going on. You don't always know the graph you're dealing with. This, I don't know if many of you would be able to look at this equation here and say, oh yeah, I know exactly what that is. That's a hyperbola, and it's centered around here. But here's just a little summary of what we found in the first few parts. This is the graph. That's the hyperbola that we're dealing with. We wrote the equation of that tangent line at 1, -7, the point of tangency, and then we plugged 2 in part B into that tangent line, and you can see we got -17/3, which is -5 2/3. And you can see that, and if you really even compare that, it's pretty close to the curve, but you can see it's an overestimate because this whole portion of the hyperbola is concave down. And so there you go. I just always think it's very important to confirm these things visually while you're studying, while you're learning, because it just helps with your confidence in your answers, that you're not just memorizing some facts and things like that. So okay, part D here. Now we'll take a bit of a change of pace, Part D says this curve has exactly two horizontal tangents. Write the equations for each of these horizontal tangents. Okay, so again, this is probably something you've encountered throughout the year in calculus. Horizontal tangent lines, what is the slope of a horizontal line? The slope is 0. And where do we get our slopes from tangent lines? We've written a tangent line in part B. We get the slope from the derivative, the first derivative, that is. So we're really saying, where does the first derivative equal 0? And they're telling us that this has exactly two horizontal tangent lines. So I should be getting two solutions from this. So again, just to reestablish, since it's on 3 screens ago here was the derivative I found in part A. When I set this equal to 0 to say where does this thing have a slope of 0, you end up setting a fraction equal to 0. And I mean, this is basic algebra, but that's really what a lot of people mess up. When you're setting a fraction equal to 0, you're really saying where's the numerator equal to 0, right? Because that's when a fraction is 0, when the top's 0. So you're really setting that numerator equal to 0, or saying where does 2x minus 6 equal 0, and that will happen when x is equal to 3. When 2x equals 6, divide by 2, you get x equals 3. It says write the equations of those, and it says I'm supposed to get 2. Well, when you need to write the equation of a tangent, you need the point, right? I already know the slope. In effect, it's 0, but I don't have the point. Well, where do we get the point from? The y-coordinate, that is, to pair with that 3? From the original function. So I'm going to take this original implicit equation and plug 3 into it for x, and find out, what are the y values that pair with an x value of 3. So here we go. We're just going to substitute this right in. Y squared minus 2 times 3 squared plus 12 times that x value of 3 plus 8y is equal to 3. And let's find out what's y. That's what we're after here. So here we go. We got some just good old-fashioned algebra 1 here. So 3 squared is 9. 9 times 2, so that's minus 18, plus 12 times 3, that's 36, plus 8y equals 3. We got ourselves a nice quadratic here. And let's bring everything to one side, and hopefully let's try to factor it. If not, quadratic formula. So let's group these terms. 8y, negative 18, and 36 is positive 18. When I subtract 3, that's going to be plus 15. And now that is factorable, right? Multiplies to 15, adds up to 8, positive 5, positive 3, which means our solutions are negative 5 and negative 3. And so those are two separate points. Each one x is 3. When x is 3, y is negative 5, and when x is 3, y is also negative 3. And each one of those are going to have its own tangent line. Now the slope of both of these, remember, is 0. That's what kind of started this off. So if you really want to use point slope form, you can. You could say y plus 5 is equal to 0 times x minus 3. Likewise, you could say y plus 3 is equal to 0 times x minus 3. But, you also could just think logically that 0 times all that's going to drop out. You're really talking about the line y equals negative 5, and here all that drops out. You're left with y equals negative 3. They're two horizontal lines, right? That's what the equation of a horizontal line looks like, is y equals a constant and y equals a constant. And those are our two solutions. So there we go. Again, I'm going to bring that graph right back just to, provide a little context for what we just found. If you remembered what the original graph looked like, it's this hyperbola, kind of looks like two boomerangs. And yeah, there's two places where it's got a horizontal tangent, one right here and one right here, both having the same x value, lined up when x is 3, but two different y values. So that one is y equals negative 3, and that one is y equals negative 5. All right, so we have probably done enough, that would be on an FRQ. They don't usually have a part E. but I'm intentionally just throwing in an extra one because, I don't know exactly what they're going to ask on any given one, so you do a little over preparation here. And they still throw probably a curveball at you just to see if you can think on the spot. So these are 5 like good parts to review some of the popular things I've seen throughout the years. So we just talked about horizontal tangents. Now they're asking, does this curve have any vertical tangent lines? And if so, write their equations. And if not, justify why not. So again, you are talking about using the derivative, which was 2x minus 6 all over y plus 4. The flip side is that, what do you know about slopes of vertical lines? You know that the slope of any vertical line is undefined. So you're really saying, again, the slope of a tangent line comes from the first derivative. So where is the first derivative? I shouldn't say equals, but where is that first derivative undefined? That's what you're looking for. And when you are talking about a fraction being undefined, a fraction is undefined when you divide by 0, right? So we're really saying, where does that denominator equal 0? And this denominator is going to equal 0 whenever y is -4, right? If y is -4, dy dx is going to have 0 on the bottom, is therefore undefined, and that means the original is going to have vertical tangent lines. So, I mean, does this seem perfectly good? We're done? Hopefully not, because this is saying, the derivative will be undefined when y is -4, but do I actually know y is -4 on this function? Is there ever a point when y is -4? And they're asking me to write the tangent lines equations anyway, so I'd really want those x values. So we're going to do a similar thing that we just did, and I'm going to plug -4 in for y and solve for the corresponding x values. Let me just get rid of that, sorry. Okay, so I'm putting -4 in for y and trying to determine if this even exists on the curve, and if so, what are the x values that go with it. So simplify here, and we get 16 minus 2x squared plus 2x. Oh, sorry, that's a 12x. We just realized that. Yep, okay. Plus 8 times that y, so that'll be minus 32 is equal to 3. And now we're talking a quadratic again, so let's move everything to one side. I'm going to move everything to the right side just so my quadratic term is positive. So move that to the other side, 2x squared. That means I'm going to have minus 12x. 16 minus 32 is negative 16, and when I add that to the other side, it's going to be plus 19. And you have this, which does that factor. It's got a leading coefficient of 2. If you remember how to check, maybe you can run through the combinations. 19 and 2 are both prime, so there's really not many combinations here, but 2 times 19 is 38. Does anything multiply to 38 and add up to negative 12 there in the middle? And no, those are the only 2 things that multiply to 38, so that just tells you this is not factorable. So I'm going to use the quadratic formula to solve this. And I can't really, I don't know if I've ever seen a quadratic formula have to be used on an AP exam, but I also looked to see, is it explicitly stated that it won't be? And I haven't ever seen it. So I think it could be, but I've never seen it actually used, and why not? You learn it in Algebra 1, use it here and there, you should be able to whip it out whenever you need. So here we go. X is going to be equal to negative b, so that's going to be positive 12, plus or minus the square root of b squared, so negative 12 squared, that's going to be 144, minus 4ac, 4ac, and a times c, 2 times 19, that's 38, and you're all divided by 2a, and a is 2. So here we go. If you need more work on the quadratic formula, there are many, many videos you could find for that if I'm going through this part too fast. Hopefully not the case. But yeah, now you're doing 144 minus 4 times 38, so that's 120, and 32, that's going to be 152. And right here, you should really see, I'm going to really drive it home here, that 144 minus 152 is negative 8. And that, my friends, tells you that there are no real solutions to this because you've got a negative inside of a square root there. So that's an imaginary solution. And in the context of this question, it was, are there any vertical tangent lines? Well, the vertical tangent lines were only going to happen when y is -4, and what we just found is that there is no x value, real x value, that pairs with y being -4. So no, there are no vertical tangent lines. Again, since y can't equal -4, but I don't think that's really necessary to add. And there we go. Pretty good variety of solutions here. And just to bring that graph back one more time, if you remember what it looks like, maybe that already spoiled the surprise while you were starting part E, that you didn't feel you need to do it. But there is no place on this graph where the tangent line is going to be vertical. So it shouldn't really be a surprise since I showed you the graph earlier, but still everything would be done algebraically on the FRQ. So there we go. A bit of a long video there, but lots of quality stuff in there. I don't want to cut anything out. So if you keep thinking of anything, if you look back at previous FRQs and you see similar things, take a look at them. Each one might have its own little curveball. And if you got any questions, let me know. But otherwise, keep working hard and hang in there, kids.